Hello everyone. This is the video lecture that covers everything we covered on Tuesday and Wednesday, and if you were in the third period, then it was probably covered on Thursday, September the 22nd. And this one covers water analogy for electric circuits and short circuits, things like that. So first, I want you to imagine this situation. You have a system of pipes that's going to simulate how your electric circuit behaves. So we're going to compare our system of pipes with a regular electric circuit. So first, I'm gonna draw myself a little box, and I'm gonna call that box a pump. So I'm gonna go ahead and type that in. This is a pump. Okay. So here's my pump, and then I'm gonna have pipes. So this is how my pipe's gonna go. My pipe's gonna go around just like the electric wires go. Here are my pipes. And of course they are connected, unlike my pipes, so pretend they are connected. And pretend they have the same diameter. Okay, so I have pipes, I have water flowing in those pipes. And the water is going that way. Okay, so the water is going that way, this way, this way, this way. Okay, that's how my water is going. So I want to compare this water circuit to our regular electric circuit. So one thing you will notice that pump creates pressure. It creates pressure, and that makes the water rush out of the pump. That's why the water is moving. So we need something that does exactly the same thing in our electric circuits, and we know that something, that pressure is voltage, right? Voltage is what makes electrons go. And the device that actually creates voltage in our particular case is a battery. And this is a circuit symbol for the battery. You have a long line and a shorter line below, like this. This is a circuit for the battery, and I'm going to extend this one a little because it's, there we go. Here's your circuit for the battery. Okay, and I'm going to connect it exactly the way I have connected my pump so far. Okay, so I have in my circuit only a battery and nothing else. That's all I have. And that actually gives me a bit of a problem because I can't really have a working circuit like that. And the reason for that, I want you to imagine that water in that pump. The water is rushing out of the pump. It's going around the circuit like so. And it rushes into the pump, and then the pump accelerates it even more. So every single time it goes through, it goes faster and faster and faster and faster until the pump breaks down. There has to be something. There has to be something in there to slow the pump down, to slow the water down. And that something is, of course, a resistor. So I'm gonna add a little resistor. So I'm gonna go ahead and I'm gonna draw a sponge. And pretend, guys, that I didn't actually go outside the pipe. Okay. So I'm drawing this sponge. It's a sponge, let's say I got it at Dollar Tree or something. And the sponge is slowing down the water. It's glued to the sides of the wall, so it can't really move. And the water has to go through the sponge. There is no other way around it. It has to go through the sponge. You know, sponge makes a very nice filter. It can't really go very far. So let's label this. This is my sponge. And sponge is, of course, doing exactly the same thing as a resistor does. It slows down the current. That's its job. There we go. Sponge resistor. And I'm going to go and erase this a little bit. Just a little bit, because I want this to, and reconnect this. There we go. Okay, there we go. So I also need to put in resistor inside my regular circuit. The battery is going to have exactly the same problem. Here's my battery. Battery is going to have exactly the same problem. Unless there is a resistor somewhere in the circuit, that battery is going to eventually overheat, and yes, it will blow up. If it's an acid battery, we're probably not going to use those in class. But even regular alkaline batteries, they pop and the chemicals come out of them, and it's unpleasant, and your battery is gone. So we do need a resistor. So I'm going to go ahead and add a resistor right now. I'm going to erase this. And now I'm going to grab myself a pen and here's my resistor. Okay, it's really hard to draw. Okay, so it's really hard to draw. Give me 1 second. Okay, so I'm gonna erase this and try again. So here's my resistor. Okay. All right. So this is my resistor. It's a very terrible picture of a resistor. The circuit symbol for resistor is zigzag, which I'm having a lot of trouble drawing apparently today. So let me try again. Okay, that's much better. Okay, so this is a resistor. And this is the regular circuit symbol for resistor. So this situation where you have no resistor whatsoever is something called a short circuit. And the short circuit is literally a path of the least resistance. And I'm going to put that definition right here. In most cases, the path of least resistance really means path of no resistance. Okay? And I want you to think about it this way. If you had a choice of going to Miss M's classroom and doing work every day and getting an A, which you do, of course, right? And then you had another choice where you don't have to go to school and you will just get an A anyway. I mean, it makes perfect sense to not go to school, right? So that would be the path of least resistance. There is nothing to overcome. There is no work to be done. Every single time an electron goes through a resistor, that electron has to do work. It has to overcome the resistance that the resistor is giving it. Now, if he has an option of not going there, then there is nothing to overcome. So I want to show you a circuit that was basically made famous by my students last year, because I've seen it so many times, and it's a very long circuit, of course. But I want to show you this mistake so that you don't make it right away. So here's my battery, and I'm gonna draw one resistor, and now I'm gonna draw another one, and yes, they're connected right here. And here's the third one, but there is no resistor, there is just a wire. So what would happen if you were to build a circuit like this? You have two resistors and you have a battery. Well, what would happen, all of your electrons will never even go into these two resistors. They will all take the route around the resistors and just not go anywhere. Because there is no point to go through a resistor if you can avoid it. So in a very real sense, it would be like this part of the circuit does not even exist. Okay? I don't want to actually cross out that side. It's as if those two resistors are not there. Okay? So it's just going to go and take the path where there is no work to be done. So that really is all I wanted to say about short circuits and water analogy. For now, we're going to revisit water analogy at some point when we're going to talk about diodes, and that is coming up pretty soon.